So a point is moving along the graph of a function, y equals 1 over 7x squared plus 4, such that dx dt equals 5. That means that the change in our x in respects, or with respects to time, is going to be 5 centimeters per second. Find dy dt when x is equal to 2. So we want to know find the rate of change of the y with respect to time. So if you kind of think about this here, I mean, just so that we kind of have some kind of a conceptual understanding of what's going on right here, so you just don't do the problem because that's the way we do it. No, right. So let's just say that this is the way that our graph looked. It probably has nothing to do with that, by the way. And then say if this is my little dot right here. As the x moves along this graph right here, right? As it moves along, it's moving at 5 centimeters per second. That's what this means. It means change in x right here from this point A to this point B, maybe, or something like that. So from the change of my x with respect to time, it's going to be 5 centimeters per second, okay? But what's happening to my change in y as you go from like here to here? Okay, as time is changing, how fast is my y changing? And so that's what that's going to tell us right here. That's what this is asking us, is how fast is our y value changing? Okay, at a given time, actually. I mean, they're asking us at a point 2. So it seems that if you want to know when something is changing, we're going to need to find the derivative, correct? So if we're trying to find dy dt, it means let's take the derivative of this whole thing with respects to time. So if I take the derivative of y, so dy over dt, okay? Again, I'm taking the derivative with respects to t, not with x and not with y, okay? Let's just do this real quick. Just note that this is the same thing as 7x squared plus 4 to the power of -1, and I'm going to use that right now, okay? So if I take the derivative of this, I would bring down to -1, right? And then now 7x squared plus 4 to the power of -2, right? But now this is my u. I'm using the chain rule. If I take the derivative of this guy, it would be times 14x. Well, let's remember, I'm taking the whole derivative with respects to time. So I have to tack on a dx dt. This is basically an indicator to us that the derivative that we just took was respects to time, not with respects to x or y. And this is helpful to us because, what do you know? Look at this. Aha! Dx dt is 5, and we're going to do some substitution here in a minute. So to kind of clean this up, I can send this in the denominator. So I have -14x times dx dt all over 7x squared plus 4 to the power of 2. Okay, so basically I just kicked this guy downstairs and left my numerator on top. So now look, I could do some substitution. I can substitute x equals 2 right here and right here. And I could also do a substitution. Oops, see if I can get this real quick here. I could also substitute dx, oh, it's kind of dark there, dx dt equals 5 for dx equal 2 right there. So basically, if I do all that substituting right there, it's going to give me my dy dt, okay? So let's see if I can get my right marker right there. Let's do it then. So this whole thing is -14 times x, which was 2, times negative, I think it's a positive 5, right? Dx dt, that's supposed to be a t right there, by the way, sorry. Dx dt, 5, all over 7 times 2 squared plus 4, and you're going to square that whole guy. So doing all that calculations, mumbo jumbo, la la la, we finally get -35 all over 256. So it's actually a really, really small number. And we kind of figured that the y would be changing a lot smaller if the x is going to be changing greater right there. Okay. Let's go on to the next one here, to number 8. Find the This is an area problem here. Okay. So the radius r of a circle is increasing at a rate of 2 centimeters per minute. Oh, so the radius is growing 2 centimeters per minute. Find the rate of change of the area. A, when the radius is 2. So I want to find out when the radius is 2 centimeters, how is the area changing? At what rates? Is it changing greatly? Small? I mean, how big or how small is this thing changing? And that's the power of the derivative that's going to help us right now. Okay. So first of all, the way that you do any of these problems is that we have to find some kind of relationship between R and A. And we also know that because it says it's an area of a circle, that A equals pi r squared, right? Nothing big right there. So it says find the rate of change of the area. So wouldn't that mean dA, find the rate of change with respects to time, right? We want to know as time is changing, how is that going to change the rate of our area? So let's find the derivative of the area, right? And that means I have to find the derivative of the left side. So if I find dA dt, that equals 2. Let's say I bring down the 2, so I'm going to have 2 pi r. But wait a minute. I'm taking my derivative with respect to time. So I have to tack on a dr dt. So dr dt. Now, once again, by some substitution, I know that the radius is 2, so I can plug in the r as 2. And they tell me that the radius is increasing at a rate of, right here, so this is our dr dt at a rate of 2. So basically, I could plug in 2 for r, and I can plug in a 2 for dr dt, and we get 8 pi, and I guess we're going to say centimeters per minute as our correction right there. And that's it.